Hello, this is Huey Din, and I'm presenting machine learning on phase field models of sea ice fracture. This is joint work with <silence> Georg Stadler, and Joanna Stiència. Our work is part of a larger MIRI program funded by the Office of Naval Research. We thank ONR for funding this work. We're interested in fractures on ice flows. Flow scale fractures impact flow size distribution, lead formation. In turn, these and other sea ice processes impact global climate. In the top left, we see that flows exhibit a variety of different geometries. These geometries are important because corners tend to nucleate fractures through concentration of stress. In the bottom left, we see flows of different thicknesses. These thicknesses cause variations in oceanic and atmospheric forcings, also potentially leading to stress differences and nucleations of fractures. In the same way, the different elastic properties seen in that we would expect to see in that ridge in the bottom right image would also lead to different nucleation of fractures. And in the top right image, we see a very complicated network of fractures on ice flows. Our goal in this project is two parts: to come up with a model that can inject some physics into a model of flow scale fractures that produces complicated fracture networks. In this way, we can study how the physics leads to complicated fracture networks. In addition, we would also like to develop a machine learning framework which is capable of predicting features of sea ice fractures. Outside of our MIRI, this framework could be extended beyond phase field fractures to other fracture models to see what could be inferred from those models. Additionally, within our MIRI, we can use this framework to inform fracture processes and discrete element models of interacting ice flows as they drift in ocean and atmospheric advection. We use linear elasticity to model our flows. Flows are represented by a domain omega. On this domain in R2, we prescribe a displacement field. From this displacement field, we calculate the strain, and we get the constitutive law by relating this to the stress using Lemay parameters, in this case, gamma and mu. The gamma and mu describe the stress response to the hydrostatic and deviatoric strains. Additionally, we also have this psi function, which will allow us to relate this to the equations for linear elasticity. So if we integrate the psi function over the domain, we have a functional for u. Minimizing this functional, finding the u that minimizes this functional solves the linear elasticity equations. One can see this by solving the Euler-Lagrange equations for the elastic energy. Finding the Euler-Lagrange equations for the elastic energy yields the equations for linear elasticity. To begin our investigation, we choose sea ice Lemay parameters that have been empirically observed. In this case, the values that are given in the bottom of the slide are values observed at -16 degrees Celsius for polycrystalline ice. To introduce fractures into this energetic formulation, we consider a crack set. Along the crack set, the displacement is allowed to be discontinuous, and the crack set is of Hausdorff dimension 1, meaning something like this line in the blob that's given there on the bottom. So we define a new energy functional in terms of the displacement u and the crack set gamma. The first part of this energetic cost is the elastic energy described before, except now the u that we're minimizing over is allowed to be discontinuous over gamma, a larger search space. And we also have, following that, the surface energy. In this case, this integral along gamma, the arc length of gamma, times the fracture toughness as a cost to break the material. In this case, we want to say that we're looking for the crack set and displacement field that minimizes this energy. Well, this is quite a difficult problem because we have gamma, which is something with Hausdorff dimension 1 and something that's 2-dimensional. And not only that, gamma also changes the sets of discontinuities that U can vary along. So the standard methods probably will not work for this. And it would be quite difficult. And as a technical note, just to make, as a starting point of our research, we choose the fracture toughness to be about 200, but this can vary wildly in empirical experiments, in empirical observations. Typically changing with temperature, porosity, grain structure, as well as the nature of the fracture. But to return to the point about how this energy functional is hard to minimize using standard methods, we can regularize the problem by smearing out the fracture set. You can see a sort of a caricature of that in the right. We do this by introducing a phase field, which takes the place of the crack set, and a regularity parameter, which controls how smeared out the crack set then becomes. As a technical note, as the regularity parameter L approaches 0, we're able to relate the 0 set of the phase field to the minimizing crack set. The phase field takes value of 0, where between 0 and 1, 0 where the material is completely broken, and 1 where the material is completely undamaged. And in this way, we construct an energy functional which mimics the behavior of the previous energy functional. The first term in the energy functional, the elastic energy, has an s squared plus eta e multiplied times the psi function from before. And in this way, we mimic the discontinuous behavior across gamma. So epsilon E is a residual elasticity and is only there so that we avoid having 0 elasticity at any point. The reason being is because this causes our numerics to break down. It's just a very small value. Whenever S is equal to 0, we see that the contribution at that point is very small to the elastic energy. So the material is allowed to bend, or the flow is allowed to displace a lot more without penalty. In this way, it's allowed to be closer to being something that's discontinuous. The next term, the surface energy, also mimics the behavior of the previous surface energy. So in this case, whenever S is equal to 1, we see that the first term inside the inner grand is 0, and it's very likely that the neighbors around it will also be equal to 1, assuming that the crack set, the 0 set of the phase field is a fairly small set, which is also something that this formulation should prefer. Given that the gradient term is going to be 0, and that contributes nothing. That is to say that away from the 0 set of the phase field, we don't have any contribution to the elastic energy. And whenever the elastic energy is 0, we see that the first term inside the integrand is maximized, and typically around places where S is equal to 0, we expect to see fairly sharp gradients. So the surface energy is maximized around places where S is equal to 0. And this way we recover the behavior. Now, the energy functional L sub E is convex in U if S is fixed, the phase field is fixed. And it's convex in the phase field if U is fixed, but it is not simultaneously convex in both. So while we have more regularity and we can use more standard methods, we still don't have convexity to use easily applied methods. But in this way, we're looking for the minimizing U and S to solve. We want to find the minimizing U and S to find the crack set that costs the least amount of energy and the displacement set that costs the least amount of energy. So for our numerical implementation, we want this regularity parameter L to be fairly small so that we're close to the problem of the original crack set. And we also want S to be to be 1 along the boundary to avoid premature nucleation of cracks along the boundary. Whenever we minimize E sub L, we have to minimize we have to fix S and then minimize U, and minimize U while fixing S because we want to be able to take advantage of the convex optimization in each of the variables. So we use a staggered algorithm wherein we fix S to be 1 everywhere at first and then solve for U. Then we use that U to solve for S. And we continue this until the differences between the iterates of S are less than a tolerance in some norm. In this case, we use the L infinity norm and a tolerance of 10 to the minus 8. We also need to choose the finite element mesh to be fine enough and the residual elasticity to be small enough. But this is pretty well studied in the numerics of these phase field problems. And to begin, we want to use fairly simple boundary conditions. In this case, we want to use a no traction boundary condition, that is no stresses in the normal direction along the boundary. And in these idealized flows, we want to fix the right side and then displace the left edge to simulate compression and shearing. So dx here will simulate compression and dy here will simulate shearing. In addition to this, we also want to introduce linear weaknesses into these idealized flows. So in the bottom right image, in the bottom images here, we in the yellow regions, the lemay parameters are the values that we chose earlier. And in the blue regions, the material is weakened to about 1/10 of that value. And this is meant to represent something such as where a flow may have just recently healed or something like this. In the first experiment, we want to shear a square flow. So in this case, we have a kilometer by kilometer square flow, and we shear the left side upward by 20 meters. The linear weakness is a diagonal line that runs through the material and moves diagonally upward to the right. In the following slide, we show the phase field results. And we can see here that whenever the weakness is not in the middle of the material, we have a very complicated fracture pattern as seen in the top left. And as the weakness moves through the material, the fracture follows the weakness as we would expect from a flow. And we can see here that when the weakness moves from one corner to the other, the fracture occurs completely along the weakness. And we see some symmetry as the weakness moves to the top right. Plots of the surface energy reflect this. So the surface energy is a measurement of how long this fracture set is. So we see here that on the left and right, we see a much higher surface energy than everywhere else in the domain, corresponding to the two fracture lines that show up on the left and right sides. And in the middle, we see this is the lowest point where we have one clean fracture through the middle of the flow. But it's quite interesting because we have both continuous and discontinuous behavior in one plot, and we would like to capture the entire range of behavior, which can be something very difficult. We want to run a few more experiments. I'd like to go over a few more experiments to show what else could happen. So in this case, we have a tent-like flow and we want to compress it. In this case, the weaknesses are vertical lines that run from left to right. As we run the vertical lines from left to right while compressing the tent-like flow by 2.5 meters from the left, we see that a fracture occurs whenever the weaknesses are closer to the edge, but as we move into the bulk material, fracture does not occur. What's going on here is that as the weakness moves into the material, it's still concentrating the stress, but since there's more material, it's harder for the material to become fractured. We see this reflected in the surface energy. We see here that as the weakness moves into the material, the fracture does not occur, and we see a much lower value than the case where the fracture does occur, as we see very discontinuous behavior here. And the behavior becomes different as we compress the flow even more. So in this case, we compress the flow by 2.75 meters. Sorry, I didn't mention this earlier, but the length of this tent-like flow is 2 kilometers and the height is 2 kilometers. But anyway, so the weakness that I'm applying here is the same. And we can see that the fracture also occurs along the weakness whenever it's close to the edge, and it appears deeper in the flow as it's moving through. But whenever the weakness is in the middle, the fracture jumps back to the left edge. And we expect symmetry in this problem as well. So what we see here is sort of what we expect as well. So the fracture increases in length as it's moving along the tent. It corresponds to an increase in surface energy. And then somewhere along the way, it hits a flat region where the fracture was the one that we saw sticking to the wall. So we see a very large, interesting range of behaviors from some very simple physics that we put into this model. But now we want to begin developing a machine learning framework to try to understand it, to try to perform inference on it. So one of the first candidates that we considered was kernel ridge regression. The reason being is that the output data that we're getting is fairly complicated and fairly high dimensional. This could be the fracture profile or these very discontinuous looking functions that we see. So to set up kernel ridge regression and why we want to consider it for high dimensional data, first, kernel ridge regression considers whenever you have two covariates, in this case, xi being the inputs and yi being the outputs, and a feature map that maps the inputs to a higher dimensional feature space. In this case, it could be each data point could correspond to a function, or it could correspond to the entire fracture profile, which we imagine to be very high dimensional. Then we also have a cost function. In this case, we see here that in the first term of the cost function, we're trying to minimize the residual between linear combinations of things inside of the feature space. Again, something that's very high dimensional. In this case, it could be the same dimension as the amount of data that we have. In this case, this is very prone to overfitting, in which case we want to penalize that somehow. And this is where this regularity parameter comes in. So the weight parameter, the weight vector controls, the weight vector encodes the linear combination of things inside of the feature map used to minimize the residual in the first part of the cost function. The regularity parameter is in the next term, and this penalizes the weight vector from being too large. So what happens here is that typically whenever we overfit, we have a very large weight on a single, on multiple parts of the feature map. Sorry, not of the feature map, but on the entries of the feature vector, this phi here. Okay. So to make things more concrete to what we're doing, we want to try to use radial basis functions as the feature map, and we want to try learning on the surface energy. So in this case, the inputs xi are the weakness positions, and the yi's are going to be the surface energy. And to each data point, we're going to have a radial basis function, which is this function that decays very quickly, but is centered around the data point that we use. And we also have this gamma, which controls the rate of decay. Typically, what happens here is that we pick this gamma so that it's optimal for the data that we use. In this case, we have good control over the gamma because we can control the spacing of the weaknesses. So I ran one tuning experiment and found that a gamma of 10 to the negative 4 was sufficient for our purposes, but it would be something to consider in other experiments. Then what we want to think about is what regularity parameter we should pick. But in this case, we have data that is a mixture of continuous and discontinuous. So in the case where we have a sheared squared flow, sheared square flow, bit of a tongue twister, we can see here that a regularity parameter of 1 is too harsh, and we don't see that we're not able to recover the discontinuity at all. At a regularity parameter of 10 to the negative 1, quite small, we begin to kind of be able to capture some of the behavior, and we see that at 10 to the minus 2 or 10 to the minus 3, we capture a lot more of the behavior. But again, paying a cost because now we're likely overfitting. And part of the problems with this are better seen maybe in this example here, where we have very discontinuous behavior, where we, in the compressed 10 experiments, we had a very flat region and then these large jumps right at the end. In this case, you can see sort of the same narrative where alpha equals 1, you don't really get much of a good fit. And alpha equals 10 to the negative 2, 10 to the negative 1 seem to fare a lot better. But if you look at the very base of these paraboloids, you see that there's a ringing effect in the center, in the middle of the domain. Now, if you wanted to make a prediction around that area, then you might misclassify, or you might say that there's a lot going on in that area. Because from what we see in the data, it's a very flat region, but because of the regularity parameter and the overfitting, we end up with these ringing effects. And we also see that this is also reflected in this more compressed, whenever we increase the compression in this tent-like flow. In this case, we see that the very right and the very left, we see very different patterns for the fit. In this case, it might just be because of how wobbly this this graph was whenever we made it. Okay, so in summary, we have developed a model of fractures on ice flows that allow for the insertion of local weaknesses, polygonal geometries, and edge displacements. Moreover, we can produce fairly large data sets. 80 experiments were completed in 2 hours on a 6-core hyper-threaded 8th generation Intel processor with 16 gigs of RAM on a desktop provided by Courant. For future work, we would like to expand the input space and feature maps with possibly random models or aggregate measures of Lemay fields, polygonal geometries, and edge displacements. In this case, we're more curious to ask the members of the workshop what kind of inputs they would like to see, or what kind of feature space that they would like to have considered. In this case, would a fracture profile be something that people would want to see? Perhaps maybe we could think about something else. It's very open to discussion. I would love to hear what people would like to say, what people would be curious about. In addition to this, we'd like to regress on other outputs, such as maybe the number of post-fracture components or dominant direction of fracture. We're also very interested in learning what people would like to see regression on. In addition to that, we would also like these methods to be general enough to work for multiple different types of models. So we would also like different types of fracture models. So we would like to learn more about your fracture models and how the frameworks that we're developing could be used with them as well. In addition to this, we want to develop validation techniques using real and simulated fracture data. So we would also like to know from the community what are the difficult cases in fracture prediction, and also what would be useful, and also if there are sources of real data out there. Or sorry, where the sources of real data are out there. In addition to what we have in access to in our MIRI project. All right, thank you for your attention. I would like to spend a couple of minutes looking over the references in case anybody wants them. My contact is given here. Please feel free to email me. I look forward to interacting with you in the DEM workshop. Thank you for your time and listening to my talk.